Alright, let's continue talking about NFAs. So recall that last time we're worried about the question about whether or not NFAs and DFAs are both talking about the same thing. They're both talking about the same kinds of languages, the same set of problems. I.e., are both representations of reg, that is the regular languages. Now, there's no independent explanation about what a regular language is. A regular language is just this kind of language that we're going to be talking about, that has something to do with DFAs. Now, let's just take for granted that DFAs are like the fundamental thing. In that case, what we want to do is we want to prove that NFAs, as a higher level of abstraction, don't allow us to do more. So what I mean by that is that, like, imagine that we're talking about like the normal world, and we're saying, well, like, let's look at a hole in the ground, right? Could a human dig that? Well, a human could dig it with their fingers, with their hand, or they could dig it with a shovel, or they could dig it with a steam shovel. And in principle, no matter what tool you use, the human could still do the same thing. So inventing shovels doesn't, in principle, make it so that we can dig deeper holes. It just means that we might be able to dig them faster or more effectively. So in a similar kind of way, we're going to take DFAs as the fundamental thing that describes regular languages. Then what we want to do is we want to prove that NFAs, i.e. the shovels, don't give us more capabilities. Now you might think to yourself, like, isn't it nice to have more capabilities? And that is true. We'll get to that in the future. But for the moment, the thing that is distinguishing about NFAs is that they have the same power as before, but is somehow more convenient to use. And the way that we do that is we first prove that for all D inside of DFA, there exists an N inside of NFA where the language of the DFA is the same as the language of the NFA. Now, we already did that. It was called the convert function, and it was very trivial to do. Basically, all we needed to do was take the delta function of the DFA and wrap it in a set. Very boring. But it's more interesting to go in the other direction to prove the theorem that for all n inside of NFA, there exists a D inside of DFA where the language of that NFA is equal to the language of the DFA. Now this function we're going to call compile, and it is actually quite useful in practice because recall that we already have a really simple way to run a DFA, right? Because it's really easy to run a DFA. You just start with a string, and then you just iterate through every character of the string, updating the state as you go. In contrast, all our implementations for NFAs are quite difficult. The Oracle one requires you to know beforehand what it does, which obviously, is hard to do. And the forking one produces this potentially infinite tree, which, that's clearly not that useful. And then the backtracking one has the problem of it explores this big breadth first thing, which is, and it has to keep track of this list of all the things that it's seen before. I mean, clearly that's very hard to do. Okay, so none of those ways of evaluating NFAs is very elegant, but evaluating DFAs is really easy. So if we had some way of converting an NFA into a DFA, then that would clearly be really nice. So let's focus on that. Now, in some ways, it might seem unintuitive that this is even possible, because a lot of the NFAs that we've seen, they do very complicated things. Like, let's just go back to a really simple NFA that we wrote, the third from end is 1 machine. So in this machine, we had the A state, which we started at, and then had a loop with itself on a 0 or a 1. Then on a 1, we went to the B state, and then on a 0 or a 1, we went to the C state, and on a 0 or 1, we went to the D state. Okay? Now, the thing that's interesting about this machine is that when we're in the A state and we see a 1, we simultaneously stay in the A state and go to the B state. And that's difficult to do. Now, imagine trying to make the same problem as a DFA, this third from n does 1. Let's think about how this would work. Basically what we need to do is you don't know at any given point whether a character that you're looking at is the third one from the end, because you don't know when the end is coming, right? DFAs, like, they only see one character at a time. But what they can do is they can remember things inside of their states. So what we could do is we could set up a set of states whose purpose is just to remember what the previous characters were. And if they remember what the previous characters were, then they can just always keep track of whether the third from the end was 1. So when we start off the machine, we would start off in a situation where we don't know what the last 3 characters were because that we haven't seen them yet, right? Because it's the empty string. Now, if we saw a 0, we should just stay in this state right here because we don't care about things that are not 1s. The main thing that we're interested in is when was the last time we saw a 1? Was it 3 ago? So if we do see a 1, however, we'll draw a line right here with a 1, then that means that 2 ago was something which was a 0 or something we don't care about. After that there was something we don't care about, and then there was a 1. Okay? Now, what if we saw another 1? Well, we saw another 1, and that means that 3 ago there was something, then there was a 1, then there was a 1. And if we saw another 1, then that means that we had a 1, 1, 1, and then this should be an accepting state because 3 times ago we saw a 1. Now if we saw another 1, then we would stay in this state right here and we would loop. But now, what would happen if at this point we saw a 0? Well, at this point, if we saw a 0, then we would go to a state where we saw 1, 1, 0. And that would also be an accepting state because 3 times ago we saw a 1. And if we saw a 0 here, it would go to the same place. Okay. Now, what if we were in this state right here and we saw a 0? Well then, if we saw a 0 there, we would go to a state with 1, 0, 0. We're just taking that one right there, pushing it over 1, adding a 0 in front, and this should also be accepting. But if we saw a 1, then we would be at a state 1, 0, 1, which would be accepting. Okay. Now, let's see what other ones we have to do. What happens if right here we see a 0? Well, if we see a 0, then we're back to there because we just have 0, 0, 0. And if we see a 1, then we'd be at 0, 0, 1, which would be up here. That's what we would do on a 1. What about this one? If we saw a 1, then we'd be over there. And if we saw a 0, we'd be at 0, 1, 0. And 0, 1, 0 would be basically the same. That's actually a new state which we haven't seen before. 0, 1, 0. That would be like the same place as if this saw a 0. We'd be at something 1, 0. And we'd go there if we saw a 0. Okay. And then we need to say what happens here if we see a 1. If we see a 1, then we'd go to there because we'd be at 1, 0, 1. And if we saw a 0, then we'd go into there. And I think that's the whole graph. Okay, so this machine right here also solves the same problem as the third from n to 1, but it required us to think really hard about how to convert this machine right here. Well, we're not really converting this machine. We're just solving the same problem in a different way. We're manually keeping track of what the previous states were, what the previous characters that we saw were. This in general is a way that is pretty common inside of DFAs Because DFAs, they don't have, they're not like normal computers that have memory or programs that have variables or anything like that. The thing that they have are their states. And so with their states, they can, keep track of arbitrary information, but it's only information that was specifically, tagged in the past. Okay, so clearly it's possible to take an NFA like this and turn it into some DFA, but how could we mechanically do this? Well, the crucial thing to realize is that in an NFA, if we look at the backtracking model, or if we look at those trace trees, they have an interesting property. So let's look at a little example from this program right here. Okay, so let's look at the input string 0, 1, 0, 0. So we would start off in the A state. Okay, then we would consume a 0, and we would go to the A state again. Then we would consume a 1, and one computation would go to the A state, and the other one would go to the B state. Then we would consume a 0, that's that 0, and the A1 would stay in the A state, and the B1 would stay in the C state, would go to the C state. Then there would be another transition, each viewing the 0, and we would get an A and a D. Now that would be accepting right there. Okay. Now notice that even though this trace tree has a split in it, there's this interesting property, which is that when we go from this layer to that layer, we see the character 0. When we go from this layer to that layer, we see the character 1. When we go from this layer to that layer, we see 0. This layer to that layer, we see 0, which is the original string 0, 1, 0, 0. So even though there are different possibilities on either side of the branch, they actually always consume the characters in the exact same order. Okay, so what we could do is let's make it so that we can build a machine, and what this machine does is that its states are going to be all the states that could appear over here on the side. Now, on the left side, what I mean by that is that let's imagine a machine whose states is like a cloud. In its cloud are all of the things that could be inside of all the nodes over here. So here inside of this cloud would be AB. And over here in this cloud would be AC. And over here in this cloud would be AD. And so here we would do a transition on 0, a transition on 1, transition on 0, transition on 0. The idea here is that this cloud machine over here, what it's doing is it's representing the boundary of the trace tree, whatever the trace tree could have been doing, regardless of what's going on. Okay, so let's take this example right here and make that explicit. All right, then I'll just copy the machine again so we can look at it. So there's A with 0, 1, 1 goes to B, B on 0, 1 goes to C, C on 0, 1 goes to D, which is accepting. All right. Now, this machine is always going to start with the cloud containing just A. And the reason it always contains just A is because this machine starts off in just A. But now, in this machine, what if it saw a 0? Well, if it saw a 0, then the A part of it would stay inside of 0, and that would be it. So there would be a loop here on 0. But if there was a 1, that means that one fork would go down the A path and one would go down the B path. there would be a line right here on a 1 that goes to A, B. Okay, now if there were a 0, the A part would stay inside of A, and the B part would go to C. So if there were a 0, it would go to A, C. But what if there were a 1? Well, the A part would go to A, and it would go to B, while the B part would go to C. So we would go to a new state called A, B, C. Let's just look at that one little piece right there. That means that we have some trace tree where there's an A and there's a B. And then what we're going to do is we're going to see a 1. Well, the A is going to fork, and it's going to go to A, because we can follow this line, and it's going to go to B, because it can go there, and then the B will always go to C. And these will all be labeled with 1, so that's why the cloud has a map from AB to ABC. All right. Well, now let's look at AC. If it saw a 0, the A would stay in A, and the C would go to D. So if there was another 0, it would go to A, D. Okay? And since D is an accepting state, that means this should be accepting, because if the trace tree ended at that point, there would be some that would say yes. Okay, now if this one had a 1 though, the A would go to A and B, and the C would go to D. So on a 1, we would go to A, B, D, which would be accepting. Okay, let's look at this one, AD. If there was a 0, the A part would go to A, and the D part would go nowhere, so therefore there would be an edge back here on a 0. But if there was a 1, the D would go away, the A would go to AB, so therefore there would be a line back here on a 1 to AB. ABD, what would happen there? If we saw a 0, A would go to A, B would go to C, and D would disappear, therefore it would go back to AC on a 0. And what about a 1? On a 1, A would go to AB, B would go to C, and D would go nowhere. So therefore on a 1, we'd go to ABC. What about ABC? On a 0, A would go to A, B would go to C, and C would go to D. So therefore, on a 0, we would go to ACD. 0 brings us to ACD, which would be accepting, because it's a D state. Now what about this one on a 1? A would go to AB, B would go to C, and C would go to D, so therefore on a 1, we'd go to A, B, C, D. Circle that, because it has a D in it. We're almost done. What about ACD? Well, the A on a 0 would go to A, C would go to D, and D would go nowhere, so therefore this on a 0 would go way over there to AD. We'll go back here on a 0. What about on a 1? The A part would go to AB, the C part would go to D, so therefore we would go to ABD. We'll go over here, up there on a 1 to ABD. What about ABCD? On a 0, A would go to A, B would go to C, and C would go to D, so therefore we would go to ACD, which is that one right there, on a 0. And on a 1, A would go to AB, B would go to C, C would go to D, and D would die, so therefore there would be a loop here on 1. So what we just did is we built, mechanically, a DFA that started from this NFA, and it would, what it does is it mechanically does exactly the same thing as this NFA, but its states represent the states along the fringe of the trace tree. Now here's something remarkable about this DFA that we made. It is exactly the same as this DFA. just with different labels. Notice that there's a loop right here on the first state on 0, and then a 1, 1, 1 with a 1 loop. Okay, let's just look at that right there. So a loop on 0, 1, 1, 1, 1 loop. Okay, so that's that path right there. Every node here is really just one of the states over there, because it turns out that what we did by design right here, this algorithm that I just showed you, does mechanically here. Let's just use a little example. Let's just follow a path in here and see what would happen in the trace tree. So let's just take a path. So let's look at the path that goes with 0. That's 0. That means, so we're in the A state. So we start off with A, and then we see a 0 and we get to A. Then let's do a 1 and get to AB. And then let's do a 0 and get to AC. Then let's do a 1 and get to A, B, D. Then let's do a 1 and get to A, B, C. And then another 1 and get to A, B, C, D. Okay, so that path right there, 0, 1, 0, 1, 1, 1. Okay, so clearly it should be accepted because the third thing from the end is 1. Now let's look. We start off in the A state. We see a 0 and go to the A state. We see a 1 and it forks and it goes to A and B. Then we see a 0, the A part stays in A and the B part goes to C. Then we see a 1 and the A part goes to A and forks to B and the C part goes to D. Then we see a 1, the A part stays in A and forks to B. The B part goes to C and the D part is dead. Then we see another 1, the A goes to A and splits to B. The B goes to C and the C goes to D. And we're accepting here because there's a D. Check mark. Okay, so as you can see, following any path in this diagram and looking at the states that it visits shows us what the trace tree would look like, although it doesn't show the particular edges. Here's another thing that's interesting about it. In some machines, there may be multiple ways to get to the same node from the same set of from the same input. And the trace tree would duplicate those additional nodes even though they're not actually relevant. Similarly, like our backtracking model would do that too. Our backtracking function would have like multiple ways of getting to the same string, the same state. Although, of course, our visited set would make so we only actually see one of them, but then we would discover them. And the trace tree would actually represent those. But this model allows us to remove those if they're not necessary. All right, so let's talk about how to do this systematically, meaning as a function. So this algorithm, its input is going to be an NFA, which has Qn sigma, Q0n, delta n, which goes from Qn cross maybe sigma arrow power set of Qn, and Fn, which is a subset of Qn. This, of course, is a member of Qn. And then our output is a DFA, which is Qd sigma Q0d, which is a member of Qd, and then sigma d, which takes a Qd cross sigma arrow Qd, and then Fd, which is a subset of Qd. All right. So we have to come up with a formula for each one of these things. So let's start with Qd. What are the states? So, i.e., what is the set that describes A, AB, AC, AD, ABD, ABC, ACD, and ABCD? What is that set? Well, the set is the power set of Qn. And remember, what is the power set of Qn? Okay, remember, let's put a little comment over here. X is a member of the power set of A if and only if X is a subset of A. Okay, so that means that the things that are inside of here are subsets of Qn. That is, they're sets of states. They're the things that might be on the boundaries of that trace tree. So that is exactly what we want here for this value. And what would Q0D be? Q0D would be just the set containing Q0n, because we start off in that set. Okay? Because we start off in A. All right, this is great. What would FD be? All right, FD would be any state that has a member in Fn. So Fn is the set of states that are accepting the NFA, and so as any state that has at least one of those in there would be fine. Now, there's kind of a weird math way to write this, so forgive me for writing a bunch of weird math. Okay, so basically what we would do is we would say QD inside of big QD, where QD intersected with Fn is not equal to the empty set. So that basically says you take each element of QD and then you restrict those to only the ones where QD intersected with Fn. That means where you take the combination of them and you see if it's not empty. All right. Now the last thing that we need to do is write down delta D. So delta D, recall that it takes in a QD and a sigma and returns a QD. So that means its argument is a QD and a C. And what is it going to be equal to? Well, it's going to be equal to a big union of Qn from QD delta n of QnC. So what is a big union? So recall from like calculus where you might have a big sigma which says that you take all the things. It's like calling a function and then summing everything. This is calling a function, this function right here, with each element of QD, which we're going to name Qn, calling the delta n function on it with C, and then taking the set that comes back and then unioning those all together. This right here is what we did when we were saying stuff like, okay, well, let's look at A, B, C. Well, on a 0, A would do this. On a 0, B would do that. On a 0, C would do that, right? 0 would take A to A, B to C, and C to D. Therefore, we would get A, C, D, union those together, and that gives us the set A, C, D. Okay, so that's really what this is writing down. Okay, so this right here is what we want, except asterisk. Okay, except ... for epsilon. Notice that in this discussion right here, we never dealt with the fact that delta n also has this whole epsilon thing. Because recall that inside of NFAs, we could have a situation like this, where our start state has an epsilon transition, let's write A here, over to B, and then on a 0, we go here to C, and then maybe we'll say that, on a 1, we'll go over here to D, and then when we get to, maybe there's an epsilon transition there over to here, and maybe there's a loop back to there on a 0, and on a 1, we go to state E, which is accepting. This is a weird language. I don't really know what it means, okay? But how could we convert this into one of these things? Well, into a NFA. Well, the thing to realize is that although there would be a state that, the states of the NFA are a little bit more complicated. Mainly from the fact that when we start, it turns out that we don't start in just the A state. We would also start in the A-B state because we would immediately take an epsilon transition over to B. So that means that our DFA would look like this. We would start in the A-B state. And we're in the A-B state because we come into A, and then the epsilon allows us to go over to B. Now, what would happen on a 0 here? Well, on a 0, the A part would go nowhere, because it doesn't have an edge there, and the B part would go to C, so therefore we would go to just the C state. But, right. And what would happen on a 1? Well, the A part would go to D, and the B part would go nowhere, so on a 1, we would go to the D state. But the D state has an epsilon transition over to C, so we'd really go to the DC state. All right? Now, on a 0, the C part would go to B, so there would be an edge here, 0 to B, all right? And DC, what would happen there? Well, on a 0, the D part would go nowhere, and the C part would go to B, so therefore there's an edge there, all right? What about a 1? Well, C on a 1 would go to E, 1 would go to E, which is accepting. And DC on a 1, the D part would go nowhere, the C part would go to E, so there would be an edge back here on a 1. Now what about B? On a 0, it would just go to C right there, and on a 1 it would go nowhere. So this right here is our new machine. So notice that we have these two circumstances, that we don't start exactly in A, we start in AB because the epsilon transition allows us to immediately go there. And then similarly, when we go to D, we don't go just to D, we go to DC, because D has an epsilon transition. Okay, so how do we incorporate those epsilon transitions into this formula? Well, here's the way that we do it. We're going to imagine, do I want to modify this? Let's put a little box around what needs to change. And then arrow, and we'll change this to, we're going to call a function called E and give it the set containing Q0n. All right, and then we're going to also take this thing right here, and we're going to call E on that also. So we're going to call E on the union of Qn, Qd, delta n, Qn, C. Okay. All right, now what is this E function? Notice that E takes a set and returns another set. So, let's write it on the next page. So E takes an element of Qd and returns an element of Qd. And here's the idea. The idea is that E follows all epsilon transitions. Okay, so let's think about how we could write that. Ex would be equal to x unioned with a big union of Qn inside of x, where we call delta n on Qn and epsilon. So the idea here is that we leave everything there, x, and then we add in calling epsilon at each element. Unfortunately, this definition is not quite accurate, because what if we had a situation like this, where we had A, and then there was an epsilon transition to B, and then there was another epsilon transition to C. So we need to call epsilon on all of those again. So what we really need to do is we need to take this whole thing and call E on it. But now we've come up with a function that is, recursive, right? So how do we do that? So what we say is that we want the least fixed point, the LFP, the least fixed point of this equation. We want, so if you call it with, so EX is going to be equal to XN such that, let's call this E prime, such that E prime of Xn equals Xn, and X, that's the argument, is a subset of Xn. So the idea is that we're just going to keep calling this until we don't get any more stuff. Now, in the math, it's a little bit weird to write this least fixed point thing, but in programming, it's actually really easy to do this. Here's the way that we would write our E function. So we'd have a function called E takes in X, and we're going to have a variable called changed, and it's going to start off as false. Actually, yeah, false. And then we're going to say, actually, you know what? Let's start off as true. Right, change starts off as true. Then we're going to say while changed. All right, while changed. Now I'll write the rest over here. We'll say that, first we'll set changed to false. Then we'll do for qn inside of X for qn prime inside of delta n qn epsilon. Okay, so we're going to loop through everything inside of X, and then we're going to loop through everything that comes out of this. And then we're going to say that if qn prime is not inside of X, then set changed equal to true. So the idea here is if we found something that wasn't there before, then set it equal to true. And then after that, then we'll say that X equals X union qn prime. So we'll add that thing there. So basically what we're going to do is we're going to keep looking through, and we're going to keep resetting every time we find something new. And then when we're all done, we'll just return X. That says return X. All right. So that's the way that we would write this E function in practice. All right. So what we've now done is we've shown that 7, 8, I believe. We've now shown that DFAs and NFAs describe the same set of languages, i.e. problems. All right. And that is a good place to end for now.